thank you all for being here. It's just an awesome opportunity. Thank you, of course, to the OpenAI science team, to IPAM, and to the BAMIC Institute. It's a really beautiful opportunity for us all to come together. So I was asked to talk about sort of reasoning AI and high-energy physics. And I think it's very clear that as a field, we are far behind mathematics. Of course, AI and ML has a long history in high-energy physics. We have some of the largest and most complicated data sets in the world. And so that, of course, is a very well-developed stream. But the idea of how we can use sort of reasoning models, large language models in high-energy physics, I think is really very well underexplored. If you pull a high-energy physicist off the street and ask them their ideas for a science program that builds upon this in the next few years, I think most people really haven't put together a coherent program. And so part of what I want to do today is just articulate what I think is a near future program, and also then to tell you about things that we're able to do now with the tools that we have at hand. And this talk is really inspired by this famous bitter lesson that the development of commercial tools typically outstrips all the hardest and most careful boutique in-house reinforcement learning that you can do. And so at least in my group at UCSB, we've really been trying to figure out how can we take advantage of the commercial products that are now available to help us to accelerate our science. And in doing so, I really do want to thank the OpenAI science team. I think in terms of all of the major commercial operators, the model of engaging in productive dialogue with scientists around their science is something that has been really awesome to see. And so I very much appreciate that. OK. So just to set the stage, since we're all from a variety of different fields here, what do I mean by high-energy physics? Well, there's lots of things we could mean. But I think a most useful distinction that really also helps to frame the idea of where reasoning models can help us is almost all of science is asking, what are the emergent phenomena of known microscopic physics, right? And the microscopic physics is typically quantum electrodynamics. We know that theory. We know exactly what that theory is. But it turns out that if you put lots of charged things together with photons in interesting contexts, you get all of the rich phenomena of the observed universe. And that's all very interesting emergent phenomena to study. But high-energy physics is the one discipline of science where we ask the other question, what microscopic physics are we the emergent phenomena of? Right? And that was a very different question, and so it makes the challenges very different. And I think there's a sense in which, because that challenge is very different, it is a perfect crucible also for the development of AI tools. All right, we can figure out, as we're grappling with this question, what is the microscopic theory that we're the emergent phenomenon of? This is the perfect place to test transformative technologies. So we've been doing this, sort of the modern guise of high-energy physics for more or less a century now, and it's pushed us from an understanding of atoms to several 8 orders of magnitude to the idea of the unification, for example, of electromagnetism and the weak nuclear force. Along the way, understanding the strong force. But there's a long way to go between where we are now in terms of our understanding, the detailed understanding of high-energy physics, and what we believe lies at shorter and shorter distances. So of course, there's an ultimate length scale where quantum gravity becomes essential. The Planck length, we would love to understand what happens there. But even before we get there, even before we get to a theory of quantum gravity, there's many orders of magnitude in which we would like to understand what the microscopic physics is. And the way that we've done this, just historically, to actually push in deeper and deeper to understand the microscopic theory that we're the emergent phenomenon of, is to build these larger and larger machines. So Sergey's talk was about physics where the experiments are cheap, and this is about the place where the experiments are very expensive. But the basic idea, right, is to actually probe shorter and shorter distances. You basically access higher and higher energies, and you go there directly, and that's how you understand the physics that happens at those scales. And so you can just ask, as a function of time and the energy with which we've been able to smash colliders together, there's been this incredible march. Here, the blue dots are lepton colliders, electron-positron colliders. The orange squares are hadron colliders, proton machines, and proton-antiproton machines. And you see, over time, every time we make an interesting leap in energy, we discovered new particles. These are all shown sort of in parentheses here. And that's really left us to where we are today at the Large Hadron Collider, where we've completed the standard model of particle physics, which is this complete, extraordinarily successful description of all of the known particles that we think are fundamental and 3 of the 4 forces that tie them together. And just something I want to highlight, because it'll matter later, is you'll notice that the energies of these 2 curves are somewhat different. And that's because if you want to collide protons together to make new things, you actually don't get to use all the energy in the protons to make something new. You spend a lot of the energy just blowing the protons up, and then you get typically 1/10 of the energy of the proton to make new things. Whereas when you collide electrons and positrons together, you get to use all of the energy of those particles, because they're fundamental, to do new things. And so that's why, even though we're operating these machines at lower energies, they're still competitive with the hadron machines. OK, so this is the historical path. This is how we got there. And it's not that we've solved all the problems. I apologize for whatever the slide is doing here. It's not that we've solved all the problems, but now we know that there are many deep questions about the microscopic physics that we have yet to access that we'd like to know the answer to. And so this is what animates a large part of the field of high-energy physics. So just to give you a few of these questions to set the stage, one of them is the origin of mass. So I remember as an undergraduate physics major, Frank Wilczek, who was one of the people who won the Nobel Prize for the discovery of asymptotic freedom, was coming to give a talk to the Society of Physics students, and he started talking about the strong interactions. And I said, well, Professor Wilczek, isn't the Higgs the origin of mass? And he reminded me, actually, no, most of the mass around us is because of the phenomenon of confinement of the strong interactions. Now, that's an energy scale that we probe experimentally, but we have absolutely no first principles way of actually making the transition from the theory of the strong interactions at high energies, where it's well understood and controlled, to actually where it grows strong and gives rise to atoms and baryons and all the rich physics that we see. And so even though we know what this physics is in some sense, actually being able to describe it, simulate it, make predictions is something that we still yet have full control over. Then there's also the other origin of mass I think that most of us think of, which is the Higgs mechanism, which is what gives the mass to fundamental particles. We've just discovered the Higgs in 2012, but understanding really the entire phenomenon of electroweak symmetry breaking, it's just the herald of that, and so that is a huge mission of high-energy physics. Neutrinos, we know, somehow are tied up in this mass-generating mechanism as well, but this mechanism doesn't fit into the standard model that we have, and so that's another thing that we need to understand. The initial conditions of the universe are something that we spend a lot of time thinking about, because if we look out in the universe, it's approximately isotropic and homogeneous. That's something that's very hard to reconcile unless there's very interesting and rich physics at the very beginning. And so this gives rise to the paradigm of inflation, where in some sense we're able to leverage the physics of quantum gravity in the early most of the universe. And by looking at the universe on the largest scales, we're able to probe physics at the shortest distances. The nature of dark matter, so of course most of the stuff that the universe is made of is not the stuff that we're made of. We don't know what it is, we simply know that it's there. And so figuring out what that is, and it could lie in any range of energies from the very largest energies at the Planck scale to the very largest, lowest energies, longest distances we probe. This is, in some sense, another key to the universe that we'd like to understand. The violation of fundamental symmetries of charge and parity reversal symmetry in the universe, it's violated in the weak interactions, but it appears to be preserved in the strong interactions. We'd like to understand why that's the case. And then there's a hint that even the forces that we see in the standard model, they fully unify at energies well beyond those that we can experimentally probe. And so that's necessarily something that we'd also like to gain access to. And of course, ultimately, the unification of those forces with gravity. So these are just some of the questions that we're facing. We have this very successful history of high-energy physics, but the game is still afoot. The question is, how do we go about actually pursuing this in the future, given our great successes and the completion of the standard model? And this is where it gets complicated. So right now, CERN, which is currently operating the Large Hadron Collider, its plan for the future of accelerators in the world to really advance to higher energies and shorter distances is to construct something that's calling the FCC-HH collider, which would require a 90-kilometer tunnel in Switzerland. It would collide protons together at 85 tera-electron volts, about 6 times the energy of the LHC. So this is a very interesting and ambitious plan that will help us to advance our understanding of physics at shorter distances. But it gets complicated when you plot this on this sort of Livingston plot I was showing you earlier. These are all the things that we've gotten to this point. And this is where that collider would live. So not only are we falling well short of any sort of Moore's law for colliders, but this is lifetimes of scientists, right? And so there's a real question of, can we actually continue to this idea of asking what is the microscopic physics of which we are the emergent phenomena? Can we even afford to do that anymore as humans? And just as we were starting to grapple with this question, right, which is becoming very real in the last decade, AI happened, right? And it could give you the very natural hope that the acceleration of scientific progress that AI promises could be something that could help us make progress in the fundamental questions of high-energy physics without necessarily having to wait this very long time. I think the first thing people think about when they, especially in the public, when they think about using AI for high-energy physics, they think, oh, great, we're just going to give AI Einstein all of the data we have. It's going to think very hard, and it's going to deliver us the theory of quantum gravity and grand unification. It's going to tell us what dark matter is. All those great things will be done, right? That's all we need to do. And one core message I actually want to communicate, which animates what we can do or what we should be doing, is that naive reasoning is not going to be enough. So for some very simple physical principles. Okay. So I should say naive reasoning may be enough for some problems. There's some questions in high-energy physics where if we have very powerful reasoning models, The nature of the question means that if we can apply all of the constraints of internal consistency and all of the existing data, there may be a unique solution or a few solutions, and then we will be able to really make progress. For example, thinking about the theory of quantum gravity, many facets of it has this nature. We can't build experiments that probe the Planck scale directly, so consistency is important. But for the most part, right, the issue is actually that existing data that we have is compatible with infinitely many distinct microscopic theories. Okay. So it's not that we don't have a good theory of nature of high-energy physics, it's that we have too many theories, and really the question is to sift them apart. And since this is a mixed math physics audience, I figured I'd put in a theorem. So this is just, you can see this natural consequence of what we call the decoupling theorem, which is one of the bedrock sort of pieces that we have in quantum field theory. And this statement is just that if you imagine a theory where there's some microscopic physics at some heavy scale, and then there's some low-energy physics that we really know and love, that the actual effects of the microscopic physics in terms of the low-energy theory has to be suppressed if I'm making a measurement at some low scale, some low momentum scale p. The effects of the heavy fields are suppressed by integer powers of p divided by the mass scale where those heavy fields appear. And so that means that's the sense in which if you have fixed experimental precision, there is an infinite class of distinct theories which differ in the ultraviolet, which nonetheless will look the same within your precision at low energies. Okay, so there are exceptions to this, but it gives you a rule of thumb. If you want to understand physics at higher and higher energy scales, shorter and shorter distances, you either need to increase the energy at which you ask the questions, or you need to dramatically increase the precision of your measurements and your predictions. Okay, so those are the paths that you can take to actually figure out what is the microscopic theory of nature, apart from just hoping for some reasoning and consistency. So if there's one message you take away, if you'd like to decouple from my talk after this, it's that if we want to solve high-energy physics, and I think we do, because what gets me out of bed in the morning is wanting to understand nature, like what actually makes this universe we find ourselves in. It's going to require acquiring more data and making the most of the data at hand. And so what we need is not just AI Einstein, but we need sort of AI Enrico Fermi, right? Who not only was someone who could do amazing theoretical reasoning in his own right, but also could build experiments, collect the data, interpret the data, and come up with new theoretical explanations. So Fermi is one of these great examples of a sort of soup to nuts physicist, and it's this sort of thing that we need reasoning models to do. But the good news is this is something that we can do. It's just something we have to be mindful of as we proceed. This is a talk about theoretical physics, but I do want to pause briefly just to advertise something, which is that if you wanted to say, okay, the best way that we're going to understand the microscopic theory of nature is to build increasingly powerful colliders. We're not sure we want to wait this incredibly long time that CERN has laid out for building the next proton-proton machine. You could ask, is there something that AI could help us to develop transformative accelerator technologies? And the answer is absolutely yes. So we already have two very clear ideas about futuristic accelerators which operate in fundamentally different ways from any accelerators we've ever built. But we know that the physics is sound. It's just that the leap from this physics idea to actually making and operating the accelerators requires more accelerator physicists to work on the problem than we currently have at our disposal. And so this is a place where agentic accelerator physicists could dramatically change this landscape of the colliders that we build in the future. And so these technologies, just to give you the brief idea, one of them is plasma wake field acceleration. So the reason we can't get higher and higher energy electron-positron colliders is that if you accelerate them in circles, you lose all the power to synchrotron radiation. So we think people complain about the power budget of data centers, but if we tried to build a futuristic circular electron-positron collider, it would consume all of the power that humanity has ever made. So instead, you can accelerate the electrons and positrons in lines, but then you're limited basically by the field gradients that we can construct normally. And so a way around this actually is to basically get electrons and positrons to surf on wakes that are created in plasmas. And this actually gives you incredible accelerating gradients. And the idea is that we could achieve these energies that we're talking about effectively building this 85 tera-electron volt proton-proton collider. We could achieve it in a linear collider a few kilometers long if we can figure out plasma wake field acceleration. So this is a place where AI could play an interesting role. The second transformative idea is to collide muons. So muons are the somewhat heavier cousins of electrons. Because they're heavier, they don't lose as much energy when you accelerate them in circles. And so you can build a circular collider. But again, to probe the same energies that this 85 tera-electron volt proton-proton machine that CERN is proposing, to reach those same energies, you could actually build a collider of muons that would sit, would be 10 kilometers and would sit on the footprint of the National Laboratory in the United States. But again, there are technical challenges, some things we haven't demonstrated before, how you can actually make and cool these muon beams. We know how, but we're bottlenecked by the number of accelerator physicists who can actually demonstrate this. And so these are two places, if you want to take a direct attack using AI, to do transformative accelerators, these are 2 places to go. But this is really a talk about theoretical physics. So if we set aside that possibility and we ask, well, now we know that data is important for progress in high-energy physics. We know that, OK, we can build accelerators. That's interesting. But can we do stuff that even short of building those new machines? And the main message here of my talk is that as we've really seen right now, and I think anticipate in the near future, that reasoning models and deliberative agents can serve as sort of AI accelerators that actually acquire more data in some sense and really allow us to make the most of the data that we have at hand. And so they actually allow us to, even without building new colliders, make progress in terms of figuring out the microscopic theory. So just some 3 basic points about why that is. One is to emphasize that not all new data need to be experimental. So if we have theories, sometimes actually being able to efficiently generate theory data, just make lots of predictions for scattering amplitudes of different types, for example. If we can generate those, then we can interrogate them, and we can actually find new patterns, which in turn lead to new understandings of the theory. And so this is a sort of virtuous cycle. I'm sorry, Svi, that Keynote has blurred your name here. This is something that really Svi has taught me, this virtuous cycle that you do new calculations, you generate theory data, you see new structures, understanding them gives you new methods and allows you to do new calculations. So reasoning models can both generate theory data and they can interpret theory data that's generated by humans. Of course, I think something that's been very clear is that reasoning models also have a power of spanning fields. And this is particularly valuable in high-energy physics because the sort of phenomenological physics that happens at colliders is very distant from formal field theory developments or developments in condensed matter physics. But it turns out that those developments actually have very strong bearing on experimental physics. And reasoning models allow us to bridge that gap. And then finally, really agents, deliberative agents, can get a lot more out of the data that we already have or we anticipate requiring, especially because in most cases, the problems, we know how to solve them, but we're human expert limited. And so I'll give you examples both of near future things and also right now things where deliberative agents have transformative potential. OK, so normally when we talk about accelerators, of course, we show the tunnel, and there's usually a set of magnets that goes down it. But this is the idea. We have AI accelerators to get us there. All right. So the first thing I want to do, again, if you pulled a high-energy physicist off the street and asked them what can LLMs and reasoning models do for our field, they really, for the most part, we haven't thought about it, unlike I think in mathematics. And so what I want to do first is just to tell you about, I'm calling it 6 intermediate pieces. This is, of course, supposed to be reminiscent of Feynman's 6 easy pieces, but they're not easy. But they're aspirational targets. They're aspirational targets in the sense that they're maybe not quite, there's already a sense that some of them we can make progress with existing reasoning models. But given the pace of progress, which I think even a conservative notion of the pace of progress, within the next year, I expect we have reasoning models that can actually help us to bring these into scope within the few-year timescale. And these are problems that are otherwise problems of decades. Okay. So these are at least my personally curated set of targets that I think we should be working on, among others. One of them comes from lattice field theory. So again, we have the theory of strong interactions, but we can't actually make predictions at strong coupling. So the best tool that we have to do that is numerical simulation. Right? We discretize space-time, and we simulate directly the quantum field theory on the lattice. And normally, we do that in Euclidean signature. So in Euclidean signature, the way we make predictions on the lattice is we're sampling the path integral with the appropriate Euclidean action. And so as long as the Euclidean action is real, this is a perfectly well-behaved numerical problem. And we get extraordinary data, which allows us to understand the strong interactions in places we've never been before. But in many cases that we care about, unfortunately, this action becomes complex. And so then it picks up a phase. And then predictions involve sums over wildly fluctuating phases. And basically, the computation becomes ill-posed. So this is what's known as the sign problem. And unfortunately, this happens in all sorts of places where we have very pressing questions right now. So real-time dynamics, things like scattering, in non-trivial configurations, strong interactions with non-trivial topology, in particular with a finite CP violating angle, and then finite baryon density, things that we would expect to see really in the full phase diagram of the strong interactions. These are places where we cannot reliably simulate because of the sign problem. Now, I'm not saying that AI should solve the sign problem. In fact, that's probably impossible because solving the sign problem for generic configurations would imply that P is equal to NP. But in many cases, actually, even if you think you're computing one of these things, and therefore you're bottlenecked by a sign problem, you can be extremely clever, and you can compute in a way that actually doesn't confront the sign problem. So sometimes there are simply different variables, better observables, analytic continuations of your calculations, which can avoid the sign problem, but nonetheless give you access to information in these spaces. A good example of this is you would think that scattering is an example of real-time dynamics, so it's not something to compute on Euclidean lattices. But Lucier, a long time ago, gave us actually a method for computing 2-to-2 scattering from Euclidean lattice data. It then took 30 years for someone to robustly extend that to 3-to-3 scattering. Okay, but that's because there was a small group of people who were working on the problem. And you could imagine this is a situation where reasoning models now and in the near future could make great progress. So really to figure out what is the whole space in which we can circumvent the sign problem. Second lattice problem, which I think is a great target, is to simulate chiral fermions. So famously, one way that theoretical physicists tell our barbers that we probably don't live in the matrix is that it's impossible to faithfully simulate chiral fermions in 3+1 dimensions. And so it's unlikely that whoever made the matrix that we live in would have bothered or could have the computational resources to give us a universe of chiral fermions. Right? Okay, so that gives you the peace of mind, we probably don't live in the matrix, but then it gives you this bottleneck that we cannot therefore fully faithfully actually simulate the actual physics of the universe that we live in. And this is, again, an unavoidable consequence of a theorem, the Nielsen-Unomiya theorem, which says with basic bedrock assumptions about your quantum field theory, you will always have a doubling of modes if you attempt to put chiral fermions on the lattice. Now, of course, we're in the last few decades, there have been incredible progress in simulating fermions on the lattice, using it for lattice QCD data. This always has some form of a workaround where you introduce fermions, there's some doubling problem, and then you try to develop some clever ways to basically separate out the extra fields so that you can isolate the physics that you care about. Each one has trade-offs, so they're typically tailored to the problem at hand, but decades of thinking about this has generated an interesting menu. But it's not at all obvious that we've exhausted all of the possibilities for effectively simulating chiral fermions on a lattice. One of them is that, as we've learned very recently from condensed matter physics, there's a phenomenon called symmetric mass generation, in which you could gap a chiral set of fermions without breaking the corresponding symmetries. And so the idea there would be, well, great, let me put fermions on a lattice. I get a doubling, so the fermions are no longer chiral. But then I have some form of symmetric mass generation that gets rid of 1/2 of those fermions. And so the low-lying fermions are the ones that I care about. So this is a beautiful idea, but actually putting this to work and seeing if it works in 3+1 dimensions, again, is bottlenecked by the number of current experts. And so this is something that I think reasoning models could help to contribute to. This one is very dear to my heart. This is something that I'm working on now. So the idea is that reasoning models should allow us to generalize the TÜV paradigm. So you're doubtlessly wondering, what does that mean? And in fact, if you're Googling it right now, you won't get any hits. This is a sort of message that we are building and developing in real time. But the analogy is, if you're a condensed matter physicist, condensed matter physics for a long time has lived and loved the Landau paradigm. This is the idea that the phases of matter are characterized by the symmetries that they break. This is very successful for understanding lots of ordinary phases of matter. And then starting a few decades ago, it really started getting taken out to the woodshed because there were lots of examples of phases of matter that were not characterized by any obvious symmetries that were broken. But then what happened was something remarkable over the last decade, which was there was the advent of a generalized notion of symmetries, what are called generalized global symmetries. And it was realized that actually the Landau paradigm survives. You simply have to bring to bear these new symmetries. Okay? And this has been incredibly successful in condensed matter physics over the last decade. So in high energy physics, we actually have what you might call a similar paradigm. So I'm calling it the TÜV paradigm. It's the idea that small parameters in quantum field theories are characterized by the symmetries that they break. Again, this is wildly successful, actually, in studying the theory of the strong interactions. But as we have gone elsewhere in thinking about the fundamental theory of nature, it started to fail over and over again. Maybe the most famous example is the observed mass of the Higgs boson. So it isn't controlled by any symmetries that we know about, but it's dramatically smaller than the other natural scales in the problem. And so the question is, is this a sign that this paradigm is completely flawed, or have we simply not fully understood the full space of symmetries that can act on this and other observables? Okay. So the idea behind the generalized to TÜV paradigm is to do what was happened in the generalized Landau paradigm, to actually work out the full set of symmetries that govern parameters in 4D QFTs, and then to see if, in fact, all of these apparent exceptions, including puzzles of nature, now can be understood more deeply. And it's clear already that bringing in generalized global symmetries helps us to make progress, but there are more symmetries that are available to us in relativistic theories, including symmetries that govern the kinematic information in our observables, and they simply haven't been fully articulated or brought to bear on the problem. So I'm putting the little OpenAI symbol here because this is one of the problems where I've been thinking about this for a few years, and I've always been sort of asking GPT for interesting to be a dialogue partner in this pursuit. And for a long time, it wasn't particularly useful. But really, I think within the last couple of months, it started to become very useful. And actually spanning this entire space is something that I think these reasoning models will be very helpful with. A related thing is we should actually aspire to define the standard model. So that seems peculiar. Didn't I tell you that we have the standard model? We know what it is. It's the standard model. But actually, again, the advent of these same generalized global symmetries has changed what we mean by the standard model. The idea that there's symmetries beyond the ordinary ones has actually told us that the standard model itself has certainly an additional generalized symmetry we weren't aware of. But then there's a certain class of other symmetries it may or may not have that we actually simply can't determine which one it is from the data that we have. It has to do with what you would call the global structure of the standard model gauge group. And it could be any one of several different options, and we don't know which one it is. Okay, so in some sense, we actually don't even know what the standard model is. And it's an interesting question. How would we go about figuring this out? So you do, of course, need some more data to break the degeneracy that we currently have. But what data you have and how you could go about getting it, this is something that we're in the very early days of understanding. So a systematic program of figuring out what the actual group of the standard model is something that reasoning models can really help us to do, especially because they can bring developments from generalized global symmetries into these particle physics questions. This is also relevant not just for understanding the standard model, but physics beyond the standard model. Lots of ingredients that we think might live at shorter distances actually have a very productive interplay with this global structure, but we haven't really worked out those consequences yet. So again, this is a place where they could be huge impact. This is maybe the biggest and most important one, and thank goodness Lance is giving a talk about it. So this is, I think, largely the subject of Lance's talk, but I just want to mention it here in these 6 targets. Most of the observables that we have that characterize the standard model are the scattering amplitudes and things that are constructed out of them. And the greater and greater precision with which we can compute those and compare them to data, this is in some sense the ultimate test of the standard model and ultimately determines our ability to extend our understanding to shorter distances. And we can do that in multiple ways. We can do that through perturbation theory by computing to higher and higher order. Again, most of our ability to do that right now for standard model data at the LHC is built off of ideas that Lance and Svi developed decades ago. Then there's also ways to pursue it non-perturbatively by basically applying consistency conditions of a reasonable quantum field theory plus convex optimization to actually allow yourself to ask what is the possible space of these amplitudes consistent with these bedrock principles. And both of these are places where I think there's great potential, again, for reasoning models and deliberative agents to help us make great progress. And Lance will say more about that in his talk. And I want to flag here this very lovely paper that came out recently with the OpenAI science team, along with a number of theoretical physicists, I think is a great example of generating and interpreting theory data within this space of mapping the S matrix. Okay, so we're already starting to see that this program can proceed. The last of the 6 that I want to give you before then telling you about things that are happening right now is something really exciting, which is I'm calling Run the Cosmological Collider. So again, the very earliest moments of the universe created quantum fluctuations that probe energy scales that are dramatically higher than any that we would ever hope to create on Earth. And in fact, the quantum fluctuations at that era were imprinted in the cosmic microwave background and then have been played forward through the development of large-scale structure in the subsequent universe. And so you could imagine that if we could scrutinize all of the correlation functions that are contained in that data, not just in the cosmic microwave background, but also in large-scale structure, we could potentially have an incredibly powerful probe of any physics that was around that scale of inflation. But what makes it complicated is you have to be able to ask lots of different questions, lots of higher point correlators in different configurations of this data. That's something you can do in the cosmic microwave background without too much difficulty. But when you want to bring in large-scale structure, everything that's happened in the universe since the era of the CMB complicates this incredibly. And so there's a huge opportunity here, basically, to discover new particles that were talking to the inflaton in the era of inflation. If their masses are around the scale of Hubble at inflation, then we can start to see evidence for them in the sky. But to look for that evidence in all of its power, we actually need to be able to interrogate these data sets. And right now, we're bottlenecked because there are basically 2 experts in the world who can do that full analysis. So any cosmologist who has a beautiful idea for some fundamental physics that lives at 10 to the 14 gigaelectron volts basically has to pass through these 2 people. There is, of course, a long ongoing effort to actually just analyze all this data with AI and machine learning, not in a reasoning or an agentic way. That actually is encountering some obstructions, and it may take quite some time for that story to pan out. So my bet is, at least in the intermediate term, the real path forward is to couple really deliberative agents to the people who are capable of doing these analyses to actually unleash the full power of Cosmological Collider. And Dan Green is here today from UC San Diego, so if you want to know more about this opportunity, I'd encourage you to talk to Dan. All right. So that, I think, is at least my attempt to articulate, I think, some near-term goals that would be transformative. These are problems of decades, but there's reason to think that the way these problems are structured, that near-future reasoning models and deliberative agents can help us to get there. But then for the last part of my talk, I just want to tell you some things that are amazing and transformative and are happening right now. And I think we'll see this sort of thing sweep the field really in the next few months. And that's to tell you about some particle theory agents that we've been building using OpenAI tools. Now, I should say, when I talk to colleagues about building particle theory agents, many of them say something like, well, right now, isn't it true that an actual human particle theorist is more energy efficient than an agent? Okay, and that's fine, that's well and good. But what about 1,000 human particle physicists? Okay, I think it's absolutely the case that one agent or a small collection of agents is much more efficient than 1,000 particle physicists. And so why does that matter? Well, one of the upsides and downsides of being a particle physicist is that whatever you do in your normal job, you have to be ready to drop everything at a moment's notice when you get a rumor of some excess in some experimental measurement that might be worth explaining, thinking about. So just to give you an example of that, I'll give you something which all the laughs in the room, people who were around in 2016 who know about what's called the 750 GeV excess. What it was is so the LHC had recently doubled its energy and recently started operation. The first wave of data was coming out of the LHC at this new energy, 13 TeV in 2016. And something remarkable was happening. Both the ATLAS and CMS collaborations, the two main experimental collaborations, they were looking in the diphoton final state, 2 photons. This is one of the same channels in which we discovered the Higgs boson in 2012. Basically, if there's a particle that decays into 2 photons, you see a bump on top of a falling background distribution. And they both started to see a bump at 750 GeV. So here's the bump in the ATLAS data. You can see the residuals here. And here's the corresponding bump in CMS data. So they were both seeing a bump. This was a 3.5 sigma excess, 2.5 sigma excess, local excess. They were seeing a bump in the same place, in a place where we just discovered a new particle. And the simplest models that you might try to write down to explain this were consistent, basically, with all other measurements. So this was, this could absolutely have been the moment in which we were starting to discover something new. Okay. And so this is what happened. So once this information was even rumored to come out, within just a 6-month period, 500 papers were written with different explanations of what this could be. Okay, so that's the sense. Thousands of particle theorists, right, were basically scrutinizing this data, trying to come up with an explanation and make predictions for what we'd see next. All right, and this happens, over and over again in the field. It's often referred to as ambulance chasing. It has merit, right? Of course, at the end of the day, this is how discoveries happen. And so that's why we do it, because we want to be the first to understand what's happening. And also, sometimes even when the models that we propose don't explain the excess or the excess goes away, we learn new things. We make new measurements. We ask new questions as a result. So it's a valorous exercise. OK, so it's a little hard, actually, to do this. You can't just sit down with GPT 5.2 and say, just out of the box, in a convincing way, how do I understand that data from a microscopic theory? And the reasoning is, the microscopic theory, we add some fields to the standard model. We write down a Lagrangian with some interactions. OK, that's what a theorist does. But what the experimentalist measures is this. OK, this is even a nice, cleaned up, beautified version of what they measure, right? It's a set of energy deposits in a detector, which are the result of many complicated processes that go from producing these new particles to making the signatures in the detector. And so there's a very complicated forward and inverse problem of how you go from the microscopic theory to these signatures. And given these signatures, how you go back to the microscopic theory. And so these things have to take the microscopic theory. You have to calculate the scattering amplitudes. The strong interactions take their hold, and they do all sorts of terrible things, which we just model. Then, of course, particles actually hit detectors, are reconstructed in various ways. They give us reconstructed objects. And then we use those to make these histograms. Okay. So we have tools that allow us to do all these things, but it's an incredibly complicated forward and inverse problem. As a theorist, there's, again, a set of tools that you can use, and we train graduate students to do this. There's been a lot of progress, actually, on making this incredibly effective in the modern era using AI/ML. Not even AI/ML, but actually a key step, which Kyle Cranmer here was really the person to pioneer, is even when there's an experimental analysis, you're not guaranteed that you, outside the collaboration, will be able to reproduce it. So the ability to store and reinterpret analyses by theorists is something that has happened robustly over the last decade. And then really, AI tools have started to come to bear on this problem. Again, Kyle and his group pioneered the idea that if you want to explore, for example, the space of exclusions of a new physics model, rather than doing a grid search, which is computationally expensive, you can use AI to meaningfully sample the region in which the exclusion is coming out of the data. And then very recently, starting in December, the idea that we could start to operate this pipeline with agents has begun to be developed here by the Heptapod collaboration. But the idea here is just they have agents that a theorist has an idea, and then the agents help them to run all these pipelines and generate the events. OK, so that's the state of play. But then there's an idea which Kyle, I think, articulated very beautifully in his CHEP talk in 2023, which was conceivably we could use LLMs and multimodal generative AI to actually explore the space of theories based on anomaly. So not just run this forward model or do inverse inference, but actually to come up with the theory explanations for the data. And so in 2023, this was conceivable. And in 2026, it is actual. OK. So I want to present to you, this is the world premiere of what we call the FERMIAcc. So this is meant to be reminiscent not just of Enrico Fermi, as I told you, we need AI Fermis, but actually Fermi and Stanislaw Ulam developed something called the Fermi's trolley, which was an analog computer that they used for computing neutron diffusion in the late 1940s, for obvious reasons why we cared about that at that time. So the modern FERMIAcc, what is it? Well, among other things, it's something that I've had the huge pleasure of developing with my colleagues and postdocs and graduate students at UCSB and KITP. So Amalia Madden, Indigo Valenzuela Imbera, Pratik Agarwal, and Jessica Howard, they're all here. So I'd encourage you to talk to them. And I particularly want to highlight Amalia and Indigo. Amalia was really the one with the courage to say, let's figure out where we can go with these tools, and actually to get us to do something powerful about it, and to help us to make sure that we were using these tools in the most innovative ways. And Indigo is the person who absolutely, this whole pipeline wouldn't fit together without him. So I particularly want to single him out. So what is it? Well, that's what we say what the acronym is. But the basic idea is we're using OpenAI agents coupled to these deterministic tools for collider fast simulation in some clever ways to take the entire idea of if there's an excess in an experimental paper, what is the best underlying explanation in a way that we can quantify. So the way that it works is you have a paper from the LHC collaborations. You give it to a series of agents. I'll get to this one in a minute. One of them just says, this is collisions at some energy in some region of phase space. That determines what sort of information you want to put into your event generator. There's some selection cuts that define what search you're doing. That information goes to another agent, which basically will tell the deterministic tools what to do. But the really awesome, magical, and incredible thing is the model building agent. This is the agent that actually, or the set of agents that figures out, given a bump, what is the most likely quantum field theory to explain it? And then it feeds it into this model generation. And the output of it is, this is all deterministic. It gives you event counts that match on to the selection of the analysis. And then you can ask, what is the signal significance? And you can then use that to adjust the model itself or the model parameters to come up with the best possible explanation. And of course, crucially, you can do this to scale. So you can do this for all analyses at all times. Well, it's been kind of incredible to see how well it works. Just to zoom in a little bit on, I think, the really interesting piece, which is the model builder, because this is the thing that we thought we were uniquely suited to doing. The way that it works with great success, we started just having proposal agents, which would read the paper, make a proposal. Those did OK. But as always, the idea was really actually to have some adversarial loop to pass it to a critic agent. Sometimes we call this the advisor agent, which imposes some criteria on the proposal and goes through a loop, patching and updating the proposal until it passes the selection. And once it passes, then it pushes it through the deterministic pipeline. So I just want to give you some, so it works. I want to give you just a couple of examples. So this is the one, if you went back to the 750G VXS and you handed it to the FERMIAcc, so you can ask it to make multiple runs. You can change the temperature, so you can get lots of different proposals. You can see how they all perform. And the one that, the histogram that I was looking at to use for this example, I was looking at the actual FERMIAcc output, and I was looking at it, and I said, oh, you know what, this actually screwed up. If you picked a high-energy physicist off the street and you asked them what's the best explanation for this bump, they'd say, well, it's going to be a scalar. It's going to be produced by its coupling to gluons. It's going to be singly produced. It's going to decay to 2 photons. There's the bump. There you go. So I was expecting that was going to be the model that would come out here. But actually, it doesn't have one scalar. It has 2 scalars. And so I thought, well, gosh, that's maybe this screwed up. Maybe we have to go back to the drawing board. But then you actually look at the logs. So I don't expect you to read all of this. But basically the chain of reasoning that the model building agent pursued. And it, in its dialogue with the critic, it realized, OK, first thing is if you decayed pairs of photons in the full standard model, you also decayed Z bosons and photons. Those should also be present. Since they're not present, somehow we have to get rid of that. But I can get rid of that if I actually couple to a second scalar, which is very light. It doesn't have the phase space to go to the heavier gauge bosons. It can only go to 2 photons. And now you might say, well, then you have a final state with pairs of these and 4 photons. But really what happens is this particle is so light, it's in a kinematic regime that those pairs of photons get reconstructed as single photons. So it falls into the acceptance of the search and explains why you didn't see anything else. And the agents have checked quantitatively with their model points that all of these criteria in which this would work out are satisfied. And then, of course, it pushes this whole model through the deterministic pipeline. It comes up with its best explanation. And sure enough, it's an outstanding fit to the data. So this little, these red bins, that's the signal contribution, which fits the data perfectly. So, of course, you might worry, the training data presumably has a lot of these 500 papers on the excess. So some of the brilliance here, I should say, this brilliance really actually came out of this dialogue. So you can look at the logs. It starts by proposing a mediocre model, and it really only gets here through this dialogue. So really amazing things are coming out of it. But you also might worry there was so much in the air on the internet that maybe that's why this was so successful. And I'm just here to tell you, so there's a whole host, there's about 20 papers now from both Atlas and CMS, which have few sigma excesses in the current LHC runs. Because they're just small excesses, people haven't really jumped on them. But that's great data for us. So we were able to take all of these papers, the ones that at least are reinterpretable, push them through the same pipeline, and it does equally well. Okay. So this is in real time, as anomalies come out of LHC data, these agents can come up using this deterministic verifiable pipeline quantitatively with the best explanations. And so there's no reason that this can't scale dramatically. So of course, we are building this pipeline up to validate its own reproduction of the LHC analyses. You could imagine things like when we talk about these future colliders like muon colliders and plasma Wakefield accelerators, I led an effort to build the modern physics case for a muon collider in 2021. That took 38 theorists. Okay? But you could basically do all of that with one of these agents overnight. And then you could take the same set of inputs and you could put them across any other collider that you propose to build and have commensurate comparisons between the physics reach. So all of those things suddenly become easily possible. But more broadly, right, we have deterministic tools which allow us to go from microscopic theories, extensions of the standard model, compare them to data sets, not just at the LHC or other high-energy physics experiments, but also cosmological data sets. And as far as we're concerned, it seems obvious that we should be able to use these agents to interface all of these things and really be able to do high-energy physics from quarks to the cosmos in a way that just wasn't possible because of human time limitations. But now we can do it sort of seamlessly with these agents. And so what's the beauty of that? The beauty of that is that even by the end of the LHC era, we may have a couple of fluctuations in different measurements, which to an outside observer might not look like any sort of discovery. But the ability to simultaneously probe all of these measurements with an underlying signal hypothesis is incredibly powerful. And now that's really here. Okay, so this is amazing. All right, I think I'm out of time. So just to wrap things up, I think there is a very clear program in high-energy physics, although we're behind mathematics, of things where taking into heart the bitter lesson that we should really actually embrace commercial tools and figure out how to bring them to bear against problems that we care about. I think there's great opportunities in the near future to do that. I've tried to give you 6 of them. I've tried to emphasize the sense in which the problems that we face in high-energy physics are qualitatively different because we're asking what is the microscopic theory we came from. But that allows us to bring these AI tools to bear in interesting and new ways, and hopefully is a powerful crucible for testing these methods. But the funny thing is even right now, even with the deliberative agents we have right now, we have at hand the ability to transform how we do certainly particle physics. And I was trying to explain to people, right now I'm in this period where it's kind of hard to sleep. Like I get up early and I can't go back to sleep, and I'm sort of always running on adrenaline. And I was trying to describe why I felt this way. And the closest analogy was the last time I felt like this was right in the run-up to the Higgs discovery, because you have the sense that the world is changing underneath you, but it's an incredibly exciting time, and what comes out the other side is going to be incredible. And I have that feeling now, and I just can't wait to see where it takes us. So thanks very much.